Good morning and welcome to the first talk of the day. I will be entertaining you for a little under an hour, talking about the gap that exists between code written by researchers and written by software developers. I will explain this by also looking at 2 examples from a product that I've been working on. And as you saw, I'll show you some nice pictures as well. So if it's too early for you, at least you can look at the pictures. My name is Linda. I'm originally from Aarhus, here in Denmark, where I took my degree in statistics. And the last 20 years, I've been working in the field between statistics and software development. And this field has since been called data science or data engineering, depending on which focus you take. And the last few years, I've had the privilege of leading a group of data scientists in a Swiss company. So I'll start by talking about this company, what we do, our products. Then I'll present the problem to you, or the problem that I think I'm trying to solve, with 2 examples, and talk about what solutions we have taken to deal with these problems. And of course, there's always challenges, so I'll talk about those in the end, together with you can then get the chance to ask some questions. Ava is a Swiss company. It was founded in 2014. It's quite known in Switzerland, quite admired. It has a lot of awards as a startup and also in medtech. This year it was acquired by an American company called Femtec, and where Femtec Health is a company consisting of a series of companies all dealing with women's health, everything around women's health. Then Ava is concerned about female reproductive health. So we're working with women's fertility. We have a wearable device. This is the blue bracelet you see on the picture. And this is worn by women during the night, and it collects physiological signals. So it collects the heart rate variability, temperature, breathing rate, perfusion, sleep rate, every 10 seconds. We have around 200,000 users on the app, and they each collect 1 million data points every night. So if you multiply a few numbers, you can see that we're not short on data. And all of these data, we have built different apps. The first app that was on the market in 2016 here in Europe is a fertility app, so it's helping women to get pregnant. And last year it was also approved by the FDA in US. Then we have been working the last couple of years on the contraception app, helping women to avoid pregnancy. And also during COVID, we took a little bit of a detour where we looked at early detection of COVID, based on the same bracelet, based on the same signals, but obviously not just for women, also for men. So how does this all work? Well, the ovulation is occurring once per cycle. So on the x-axis here, you see the time. So this is one cycle, and around in the middle, a woman has her ovulation. But it's actually the days before the ovulation where she can get pregnant. So the 5-6 days before the ovulation, which is marked here by green, is the day where she can actually get pregnant. So these are the days that we are trying to predict coming from the other end. So we're not, after the ovulation has happened, it is rather easy, but actually working in real time, we want to detect when is the fertile days coming up. And since this is controlled by hormones, and since hormones also influence everything else going on in the body, there's also a change in the physiological signals during the cycle in a woman. And these changes are what we are using in order to predict the fertile window coming up. So for example, it's well known that the temperature rises slightly after the ovulation, but of course temperature alone is then not enough because we want to predict it before, not after. So we're using all of the signals and how they work together. So as you can understand, there's a lot of research, a lot of medical research going on in this field. It's all new. It's not been done before. We have been doing a lot of clinical trials together with a lot of different research institutions. And also when we put something on the market, we need to test it first. And also after we put it on the market in order to find out that it's still doing the right thing. So a lot of medical research, a lot of clinical trials. And of course, to make it work as a product in an app, we have to apply a lot of machine learning. So there's a lot of signal processing, a lot of modeling, neural networks, and of course we have to deal with very noisy data at times. So we have to accommodate for that as well. For example, when a woman is ill, her temperature rises, we have to accommodate for that. Or when she has been out drinking the night before, her pulse is slightly elevated. And also if she has to do a big presentation in the morning, then she might also be slightly stressed out the night before. So all of this, of course, we have to accommodate for. And my point is, I don't want to talk more about algorithms now, or the methods that we're using, but I want to point out that this is a very research-heavy area. So the people that work here tend to be more towards the type of researchers than towards data science or data engineers, software developers. So when you want to put code written by researchers into production, it can be quite difficult. While I did my research for this talk, I found this quote on the internet that one of the hardest part of machine learning is effectively putting models in production. And I find that very true, and a lot of people agree with that. That is a very tough problem. And that is the problem that I want to talk about today. So I'll start with two examples from the contraception app that we were working on. So first of all, in the beginning of last year, we wanted to reprocess all of our data files. So this picture you see here, you can't see it that clearly, but don't worry about it. It's not important. X-axis is time. The different Y-axis are the different levels of the signals. And this represents one file. Of course, it's not a picture file, but it's actually signals in a file. So we need to parse a file, we need to split it, because it might be, this is one night of data, but it might be several nights of data. So we need to split it into the different sleep events. We need to filter the data, and we need to extract some interesting features that we can actually put into our models. Because working on the raw data would just be too much. So we extract features from it. And we need to assess the quality. And to do this, we have in production, we have a Python module that do all this processing. And the existing solution that was set up was to take this Python code and rewrite it and let it run on Spark on AWS. And the reason I don't think that's a very good solution is that Spark is it's its own language, so you have to rewrite the code and re-implement the solution, which means that you then have two parallel solutions, one for production and one for when you want to reprocess data. So what we did instead, the obvious thing is to take the Python module and run it in parallel on AWS. Of course, that then introduces some other challenges. You have to build some infrastructure around it in order to run it in parallel. But at least we're not re-implementing code anymore. Then the second problem was after we had all of our data, we wanted to retrain our model. So it was a neural network in TensorFlow, and the model itself was not the problem. It's okay the way it's packaged. But what was the problem was the data handling. Because in order to run a TensorFlow model, you have to reformat the data in a way that TensorFlow can understand it. You have to normalize the data, and you have to filter data. So between nights, there might be, as I told you before, there might be a night where you have a hangover, so you want to filter this data out. and it's called outlier detection. And also then finally, when you get a result from the TensorFlow model, you want to reformat it and put it into the output again. And this code was simply scattered all over the place, all over the training script. And in the same, when we looked at the production code, it was also all over the place. So it was very difficult to follow this code. It was very difficult to maintain it, and almost impossible to extend it to do something new and to replace the model, for example. This is a well-known problem. It's called glue code, and it's defined as supporting code for getting data in and out of generic ML packages. Some people have been calculating how much this code is and came up with a number of 95% in typical ML scripts. And it's considered an anti-pattern. And as I said, this was training, and when we looked at the production code, exactly the same thing, scattered all over the place. And it was very difficult to prove that it was the same code that was implemented in the training and in the production code. That it was the data handling was actually doing the same thing. We were spending quite a long time trying to prove that the outlier detection was doing the same thing. So again, we have this problem with re-implementation of code. So 2 issues identified. We have the glue code, the code that was used for getting data in and out of ML packages, and we have this re-implementation of code. And yeah, you can see the solution is just to write good code, right? It's, for example, don't repeat yourself, just reuse code. But then, of course, who should be writing this code that can be reused? And also, it doesn't stop there. As you saw in the first example, we might also need to have some additional infrastructure to run something in parallel, for example. And we haven't been talking about experimentation with code at all. This is just training something that exists and running something in production. But actually, when you want to experiment with code, you have to do it in quite a different manner. So let's look at that experimentation. What exactly do researchers do when they experiment? Scientists often use different tools. For example, there's one called Jupyter Notebook, which you see an example of here on the screen. It's an interactive tool. You write one line of code and you click return, and then you get your results. You can look at your result. You can run the same line of code again on the data after it's been modified, explore the data, plot the data, change a little bit, go up and change your script and run it again on the same data. So it's quite messy. There's no one single path. You can basically do whatever you want in whatever order you want. So it can become quite difficult to follow. It's an iterative approach and a lot of trial and error. And that means that we end up with a lot of different paths of code and a lot of alternative lines of code that can do different things. And often you also have to work together with other tools, such as TensorBoard, if you would like to do some training of TensorFlow models. And also one thing to notice, aside from the iterative approach that we need to take, is that scientists are typically generalists. So they really like this one solution fits all. Write really, really, really long scripts where you can change the different parameters and get all sorts of settings and use this script for basically everything. Which means that it's not specific to solving one single problem, but might be reused again and again on different things, especially when you're talking about the data handling, that you want to do different models, but you always want to do data handling, but sometimes in slightly different ways, because you want to normalize differently, do outlier detection differently, scale your parameters, or something like that. So what happens when we want to move research code into production? What are the differences between these two kinds of code, and what are the consequences of these differences? Well, as I said, research code needs to be very flexible, and usually it is, and usually it can do almost everything, whereas in production code, you want to have something specialized to solve exactly the problem that you have, which means that you have a lot of redundant code that you have to get rid of. Also, research code, you're usually using it manually. So one person sits in front of a script and executes it, often line by line, but executes it and sits over it and know exactly what's going on and can deal with all sorts of things that happens. Whereas in production, you need to run a script automated. You want to have repeated usage. So you have to focus on stability, exception handling, and unit testing in order to make it work. But you don't have to do that when you're writing a research code. And research code is typically used by one person, whereas production code, it's used by one person or sometimes a group of persons, but then at least they work very closely together and create their own code, whereas production code can be used by, or can be touched by a lot of different people. And therefore, researchers, when they write research code, don't necessarily follow best practices for writing code. And also this row-by-row execution that we, for example, saw with the Jupyter Notebook means that you don't necessarily have to follow use object-oriented programming or follow any design patterns when you're writing code, whereas that you typically do in production. And research code is mostly standalone code. It can, of course, it needs to get data in. It needs sometimes to work with TensorFlow, but in principle, it doesn't have to interact other than with the person that sits between it. It doesn't have to interact with anything in an automated way. Whereas a piece of production code sits inside of a system and has to interact with the rest of the system. So the interfaces to the rest of the system needs to be clearly identified and clean. And also, when another point with data is that in research, you work with very large data sets. So when we want to do anything in training, for example, we need to use the whole data set, all the nights of all the women that we have. Whereas in production, we just take one single night from one single woman. So instead of looking at all the data that we have, we're only looking at one single data point. And therefore, data handling is also quite different. And that also has consequences with how you parallelize your code, because when you do research, you want to first do things serialized. First, you want to get all your data. Then you want to train, and within the training, you want to parallelize it. So you want to do the parallelizing within the scripts. Whereas in your production code, you have one script that typically runs very fast, and you do the parallelizing outside of it, which means that the structure of your code is also very different, and the way you optimize your code. So I've been talking about these two different environments, and I'll come back to this slide a few times. So I made it green so you can recognize it. On the left-hand side, we have the experimentation platform or side of things. And on the right-hand side here, we have the production. So I have painted a lot of little boxes, but typically it's not different scripts that do these things. Often it's scripts that touch on all of these things. So a little bit of signal analysis, a little bit of data mining, a little bit of data manipulation, all in one big script. And then when you want to move this to production, you take bits and pieces from all of these parts that you need, and then you move a very little part of it to sit somewhere in your system. So that's the green box over here. Take a little bit of the machine learning code from over there and implement it in production. And around the machine learning code sits a lot of other code. Some of it, test and debug, I made this light green, you can't see it, test and debug, logging and data handling touches slightly on the machine learning code, but the rest of it doesn't. So there's a lot of code sitting around the machine learning code. So let's first look at what we can do with that code. So this picture looks very much like it. It's from a research paper from Google from 2005. 15, where they talk about hidden technical debt in machine learning systems. And they also call it glue code, and there's two different kinds of glue code. There's one we talked about before with machine learning, getting data in and out of ML packages, and the other one is known from software development, is to connect incompatible components, and typically it doesn't contribute towards your requirements. So that's a lot of the other boxes sitting around. So let's look at this glue code. Who should implement this glue code? Should we let researchers implement their own code in production? And where this might be some good ideas sometimes, I would generally say not really, because they don't have a big interest in it, then they probably would have become software developers instead. And also they probably don't have any skills in this area. And they should really just focus on what they're good at: research, modeling, data processing. Should we then let software developers build this code? And here the answer is always it depends. So what type of code are we talking about? Are we talking about the software glue? Then absolutely yes. There's no reason that a data scientist should deal with security of a system, for example. And if we're talking about the machine learning glue, then probably not. Because if you have to lift your code from what was implemented by the researchers to the production code, again, as I said before, you end up with parallel implementation of it. You can have hard time proving that it does the same thing, and that really suffers. Your time to market suffers from that. So let me talk about what we did with the first type of glue code in Ava. So this is our architecture on a very high level. So we have the bracelet over there, where we collect physiological data. There's some firmware sitting on it. So it sends via Bluetooth, it sends the signals to a mobile phone. And here the user can also log other things like hangover and menstruation, obviously. And all of this gets sent to the backend. The backend then deals with all the communication, user access, security, data handling, and all the business logic. For example, when the user needs to send a notification in the app telling, do you have something to log today? The backend calls different modules. The green one's over here, one for processing the signals. That was the one I talked about before. One for processing the logs that the user enters in the mobile phone. And finally, the one that actually puts this together and predicts when is the ovulation or when is the fertile days coming up. And all of this first part of it is not really anything to do with machine learning. So we have split it up in different teams. We have a firmware team that deals with the bracelet, the software and the bracelet, a mobile team that deals with the UI, and then the backend team is overarching basically everything. Of course, underneath it all, we have DevOps handling all of our infrastructure to run our application and the infrastructure for developing our applications as well. And the last part of it is where the data science team has their domain. So we deal with the modules for everything that has anything to do with the data or data handling or algorithms. And we also write in a different language than the other. We write in Python. So these ones sits in a universe by themselves, work as microservices, know nothing about state. They're stateless. They know nothing about what context they have been called from. The interfaces to the rest of the system are very clearly defined. So if we change this picture a little bit, so this was where we came from. So our implementation of it looks like this. We have separated everything that needs to get something from the left-hand side is separated in its own modules with clear interfaces to the rest of the system. And we also went a step further. So we looked at the modules that was written by the data science team, and looked at what similarities were between these modules that also has nothing to do with ML code. So we have, since it's a Kafka queue, we have connection to Kafka, we have input-output of the JSON file that it receives from Kafka. We have logging and monitoring, we have unit testing, Docker and Jenkins integration, and setup of the whole modules. So all of these things we could take out of the code and put them into some shared libraries, which is the pink box you see here. So returning to the picture, we now have separated some of the code, some more of the glue we have put out in this module that is shared. And now we want to talk about the last part of it. So how we get all of this code from over here onto this side. So this has to do with the running of training of the models and running the models when they have been trained. So ideally we should have some sort of platform sitting somewhere where we can do experimentation and evaluation of our models. That should result in some trained models that have the same format and can just be configured to be put into the production code, ideally. And luckily for us, there are tools out there to handle this. And tools for managing the machine learning lifecycle. So the machine learning lifecycle is the cycle I showed here, where you start with collecting the data, then you want to prepare your data, explore the data to find a model that you can use, and then train that model when you have found it, test and evaluate that your model is doing what it's supposed to do, deploy it in production, run it in production and monitor that it's doing the right thing, collect more data, and then do it all again to improve your models. So this is called the machine learning lifecycle. And the tools out there, the two most popular, are called KubeFlow and MLflow. KubeFlow is from Google and MLflow is from Databricks. Since KubeFlow is from Google, obviously it runs with TensorFlow and TensorFlow's own language called TensorFlow Extended. MLflow is basically just Python, so you can do anything you want to do there in Python. KubeFlow is pipeline-based and MLflow is experimentation-based, and what that means I'll come back to in a few slides. And that means that MLflow focuses on tracking experiments, where KubeFlow is more from managing very complex machine learning systems. And as the name indicates, KubeFlow runs on Kubernetes, and it's considered to be very, very difficult to set up and maintain or handle for just data scientists like me. MLflow can be run very easily locally on your own machine, or you can put it up on a cloud when you're more mature. So that means that we now have our MLflow, which was this platform for experimentation, for developing, training, evaluating, comparing different models. The MLflow comes with a built-in model registry, where every time you train a model, it gets stored to this model registry, and by just calling an ID, you can get that into your production environment. Of course, it's not that easy, because you have to make sure that the code and in experimentation and in training, if you're doing some custom models that you invent yourself, which we do, not just use the standard ones, then you have to make sure that these models are known to both systems and also the way you want to handle your data. And we have even gone a step further. We wanted to evaluate the whole system, so we also made that possible to evaluate that in MLflow. This is how it looks like. This is the desktop of, or the dashboard for MLflow. And every single line is a experiment. So here we have trained a model. You see here under models there's a link. So we have trained a model several times. We have trained it with different parameters, and then we have different metrics that we have measured that we want to compare these different models by. So for every model, we have fully insight. We know exactly how it was trained. That we can click on the link and come to a page where it's exactly described what the input was, when it was trained, and if we have stored any artifacts. In this case, we have made a plot that we have a histogram that we wanted to show. And also, if you click on the model itself, you go directly to the model registry and you can explore your models. So this is really good for experimentation. You have this model registry, and the biggest advantage is, of course, that we have reproducibility. So we know exactly we can do this again. If somebody asks us to run exactly this model again, we know how it was run, with what data, with what parameters. And the best thing is that it's really easy to deploy the trained model. Because this is how it looks like, the code. So this directory here is the stored model by MLflow. Everything is done automatically. In the ML model file, you see the model path, that the model itself was stored in a pickled file. And you see that the serialization format is also given, that it was serialized using Cloud Pickle. We have which module we should use to load the model in production. In this case, it's MLflow, scikit-learn, and also which version of scikit-learn we used. And also the rest, which Python version did we use, and all the environment and requirements are stored in files in this folder as well. And in order to unify everything so that we always have the same format, we follow the pattern from scikit-learn, which is a well-known library for doing machine learning. You have, if you here we are extending this object called class called base estimator, and by that you have to implement a fit function. A fit function is for training your model. A predict function is when you have a trained model and you want to get a prediction of it. So by these two functions, we can train in the experimentation side and we can predict on in production. And we also get all of the other advantages with the scikit-learn. We have all sorts of different models. For example, the random forest classifier. We have all sorts of ensemble methods we can use. For example, the backend classifier. We have hyperparameter search. We have scaling. We have, and the most important thing is the pipeline, which we have used, which means that you put together the way you handle your data and your model. So the example here, you can see this pipeline consists of a data smoother. So first the signal is smoothed, and afterwards it's been put into a model. This case, this model is defined up there. It's also even a grid search around it. So a pipeline, like everything else in scikit-learn, does also have this fit function. So here it's been fitted, and when we then it's stored to the model registry, and then we can just load it into production, and we're sure that we get the same smoother, the same model. Everything is set up exactly the same way in experimentation as it is in production. So where did that leave us now? We changed the left-hand side. We have this MLflow platform where we are experimenting. We have the model registry, and both the MLflow and our modules are calling the same libraries for models, for defining the models and for data handling. And the model is stored in this registry and just picked up by the production scripts. So that was it. Just to reiterate, first we took out a lot of the glue code by separating everything in the system that has nothing to do with the data science at all. Then we took out some that is touching the data science and put it into a reusable module. And then we finally took and implemented this, used this MLflow framework in order to share code between production and experimentation, and to share the code as well and get easy access to the models. And also said that there's still remaining challenges. This looks very, very nice, but you can still build a big, big mess. There's nobody's enforcing on you that you should, like we have done, use a nice structured way of implementing everything, that you separate all the code you can. You can still do whatever you want, build whatever Python scripts you want to do in MLflow. It doesn't stop you from building a mess still. I've been very fortunate that I work together with data scientists who are very skilled in programming and also very eager to do it the right way. So it's not been a problem, but if you don't have that luxury, it can be very tough, because a lot of researchers still really do not want to go down this path. They want to use Jupyter Notebook still. They want to use different tools, and it's really outside their core competences even to write something as complicated as the code I just showed you. And of course, they would need a lot of training and support, but still, some researchers would never go down this path. And aside from that, you still need the software developers to develop the rest of the system. You still need machine learning engineers to help you set up all the different parts you can't handle yourself, or write the Python code. So there's still other skills needed than just data scientists in this setup. And then, of course, you can ask what... oh yeah, and I forgot to say, it doesn't solve all the problems. The first problem I presented to you, retraining the data, is not covered by this framework, but we are doing it sort of the same idea by reusing the code. And what is the solution then? I mean, you could argue that it might be Agile, and I think that's a very good approach, that you actually put together the people with the different skills, the different comfort zones together in one team, and let them implement this together. Pairing up, writing code together, and also when you have multiple projects that are working on the same platform, you want to have people working on different projects in order to make sure that the code actually stays the same, that you don't do parallel implementations of things. So that's all from me. Thank you very much for listening in.